All right, before we get going, anybody have any questions about anything at all? What due dates are coming up? Anything we've talked about previously? All right, so our next section in chapter 2 is about implicit differentiation. Talk about what that means after we look at an example or two. But look at these three functions here. Or not, I guess I shouldn't use the word function. They might not be functions. But based on what we can do right now, can we find derivatives of, can we find a derivative of that first equation? I heard a yes. How would we do that one? Good. Okay, so if I could re-express it as y equals x cubed minus 6. Pretty straightforward. You've done a lot of things like that. What is that derivative? Yep. All right, how about the next one? So I mean, through to the first one, we can rearrange and use the power rule the way we're used to. How about the next one down? X squared plus y squared equals 25. Thomas? You said square both sides. I think you meant something else. Yep, so I can rewrite it like this. Y squared equals 25 minus x squared. And then I get y equals plus or minus 25, or radical 25 minus x squared. Is that a derivative you can find right now? If I broke it up into two different pieces, the positive and the negative. Yeah, we just did chain rule on Friday. You can make use of the chain rule for that. How about the last one, finally? So what was your plan of attack on the first two? Your first move there. Go ahead. Try to isolate y. Can you isolate y in this last example here? I gotta vote for yes. Divide by what? If you divide by y, let's see what happens there. Yeah. So then you have x cubed plus, or I'll just do it like this. X cubed over y plus y squared equals 6x. So while I don't want to say it's impossible, y, it's obviously going to be more difficult, right? So if we could find a way to take that derivative without getting involved in that, that'd be good. And that's what we're doing today. So I haven't really used the term because the term is not used ever, but when you differentiate things like this is called explicit differentiation. And we use the word explicit to mean we have two variables, one dependent, one independent. What's the independent variable in that first derivative we took? Or the input variable, like you're well. So the input variable is x. The output or dependent variable is y. And I'm taking it or to this r. What is the derivative of y with respect to x? It's this thing we call dy dx. That's what that notation means. But we can use the chain rule to now take derivatives. So we can take derivatives of all three of these things now without having to isolate a variable. We can just leave it the way it is and differentiate from there. So let's look at an example. You all agreed that we could do this derivative based on the tools that we have, but you wanted to isolate y first. We don't need to do that now. So what we're really going to do is this. I want to find the derivative of y with respect to x. So what I'm going to do is this. I'm going to take the derivative of every single term by itself with respect to x. So let's focus on the ones that are going to be pretty simple right now. With respect to x, what's the derivative of x squared? To x. We're going to leave the y term alone for a second. For ourselves some room. What's the derivative of 25 with respect to x? 0. All constants differentiate to 0. How do we deal with thing so I'm going to draw off to the side here a block diagram again. So one big assumption we make when we're doing derivatives like this is that we assume that x and y are related in some specified way. And that's always true. But when you have equations written like this, it's pretty hard to see. When you have y isolated, it's a lot easier to see. So I say all that to show you this. There's some process that x goes through to become y. That process is typically something we think of as a function. What is the relationship that maps x to y? But in this case, I'm doing something else to y. I'm taking I'm squaring. So even though it's not totally obvious, it's really not obvious at all. There's some relationship that maps x to y and then maps y to y squared. Are we okay with that so far? It's kind of the crucial idea for what we're doing in this section. So please stop me, ask me questions if you have them. But from here, you can really think of whatever this process is that turns x into y squared. That's a composite function. And since that's a composite function, so now let's start differentiating from outermost to innermost. So this outermost function, let's go actually just give names for these. G of x is equal to x squared. And I'll call this h of x is equal to y. So our outermost function is x squared, right? What is the derivative of x squared? 2x, you just did that, right? So our derivative in this case is going to be 2 times something. And that something is going to be whatever the actual input was to my x squared function. What was the input to that squaring function in this case? I heard something. The power of 2 is what the function is, right? So yeah, the output is something here. But I also evaluate that derivative at whatever that function was. In this case, it's y. So hopefully you can kind of see something that makes intuitive sense. The derivative of, let me back up. The derivative with respect to x of y squared is 2y so far. Because we have handled the derivative of this g function, the squaring function. But g prime of x is equal to 2x. So in the chain rule, I think we've handled the derivative of the outside function. The derivative of squaring something is 2 times that same something. In this case, that something is y. But now I have to handle the derivative of the inside function. What is the derivative of y with respect to x? Yeah, I mean, that's kind of a silly question and a silly answer, but the derivative of y with respect to x is this thing we've been working with for a few weeks now, this dy dx, or sometimes you'll see it called y prime, notation that I've used. So I just want to point out here, this right here is the derivative of g of x evaluated at y. And this right here is the derivative of h of x, which is really just y. I'll go ahead and pause here because I think this deserves some questions, deserves some attention. We're not done, but I think it's a good place to make sure everyone's still on the same page. Probably not any questions about where the 2x and the 0 came from, but how are we doing with that y squared term? And how that derivative unfolded. All right, if we're okay with that, I really want to get dy dx. So my whole goal here was to get to an explicit form of that derivative, dy dx. So how can I start working toward that? Right, I'll subtract 2x. So I get 2y dy dx equals negative 2x. Yep. So what I get is this: the dy dx equals negative x over y. We did. Is that in the hallway or next door? Cool. All right. Any questions on this? All right. All right, so given this, I want to find the equation of the tangent line at 3, 4. So let's jump ahead to where we already know. We know dy dx is equal to, was it x over y? Oh, so I want to find the equation of the tangent line at this point, 3, 4. So we've done a lot of this, not in this implicit context, but if I want to find the equation of the tangent line, where do I need to go from here? Knowing that I have this dy dx. Plug in the x and y. So if I want to evaluate this at 0.34, I get negative 3 over 4. So I got the slope of the tangent line. And since I have the x and y location, I can pretty much get the rest of this. So y is equal to 4. Negative 3, 4 is the slope. X value is 3. That makes b equal to 4 plus 9 over 4. That's good. Go ahead. Okay. So I have this equation, y equals negative 3/4 x plus 25 over 4. Does anyone recognize this equation, x squared plus y squared equals 25? It is a circle. Know anything else about that circle? Got a radius of 5. So if I can, nope. And we know our dy dx here, where's our point? 3, 4. So about here, our tangent line approximately looks something like that. And think about the way that, the slopes are going to act on the circle. If my x value is 0, what's my slope going to be? It's going to be 0, right? Because that means I'm on the y-axis, and that's where those horizontal tangents are going to be on the circle. On the other hand, what if dy dx is undefined? First of all, what would make dy dx undefined? What values of x and or y would make dy dx undefined? Yeah, if y, so yeah, negative x over y. So if you divide by 0, if y equals 0, you're going to get undefined. And that's where you're going to get those vertical tangents. So where the circle crosses the x-axis, you have a vertical tangent, which you can't define the slope there. Anything else about this? All right, so let's find the derivative of this. The example that we maybe thought we could isolate y, but knew that it would be much more difficult. But we don't need to do that now. So now I want to find dy dx again. So really what I'm doing is I'm just taking the derivative with respect to x of each side of this equation. So on the left-hand side, what's the derivative of x cubed plus y cubed? I better stop there. First of all, do we agree? Some shaking of heads. I have some layers. Over here on the right, let's unpack that a little bit. So if I take the derivative with respect to x of y cubed, that's going to be equal to how do I break this down? So it's the derivative with respect to x of y cubed. Having a hard time trying to break that down into smaller pieces without doing the block diagram again. So let's just think about it in terms of inner and outer functions. The outer function in this case is a cubing function. From the power rule, we know that the derivative of a cubing function is 3 times the same variable squared. So that's where this outer function comes from. And then because the inner function in this case is whatever the function that maps x to y, that's where this dy dx, the derivative of y with respect to x comes from. Go ahead. And that's how the chain rule operates. You basically take the derivative of the outer function, evaluate it with the inner function nested in it, times the derivative of the inner function. So do we feel good about the left-hand side of what we have here? All right, now let's handle the right. How was the derivative of 6xy? What rule or rules am I going to need to use here? Are we sure about that? We phrased it like a question. Why do we need the product rule? Multiply, so multiplying 2 different variables, yes, but in reality, 2 different functions. So because this is our first time in this context, let's go ahead and break this up into, I'm going to call them u and v, just to save a little space. I'll call u 6x and I'll call v y. In that case, then what is du dx? 6. What is dv dx? Y dx. So yes, you're correct. We need to use the product rule because we're multiplying two functions. Now we have all the ingredients. So this right-hand side should be 6y plus 6x dy dx. What's special? You put the 6 with the y, but really, especially since this is our first time looking through this in this context, separating x and y and really spelling out the product rule is a good move. Go ahead. This would be something I could distribute, but 6 times x times y, there's no distribution going on there. Go ahead. Sure. So why don't I just spell out the product rule again? So I'm going to take ddx, the derivative with respect to x of uv. And this is not the way that I showed you the product rule the first time. This is another way you might see it. But it's one function times the derivative of the other, plus the derivative of the first function times second. So, I mean, lots of ways you might see product rule written, but they all basically say the same thing. Take this function, multiply by the derivative of the other, and then vice versa, and then take the sum. Good questions. Anything else? Are we ready to find dy dx? Yeah, I'm not moving from the slide. We're still gonna find a. So we have taken a derivative. So the actual process of taking a derivative is done. Now we have to solve for that derivative, that dy dx. This one's a little trickier. So any ideas how we want to isolate dy dx? Go ahead. Okay, so you said a lot of things there. I'll try to unpack it a little bit. En route to isolating dy dx, we're going to get all the dy dx terms on one side. So I'll have 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. So now still have those two derivative terms, but now they're added together on the same side of the equal sign, same side of the equation. From there, I have a common factor on the left, so I'll factor out dy dx times y squared minus 6x. I left something off in there. Yep. So now that I have that factored out, now I can truly isolate it and get dy dx equals 6y minus 3x squared over 3y squared minus 6x. And that simplifies a little bit. And I'll take a pause right there. So any questions about the calculus we needed to different? And then how about the algebra we used to actually isolate dy dx and solve for it? But I'm actually not even sure which one looks most B-ish. Go ahead. So I'm assuming that your answer looks like x squared minus 2y over 2x minus y squared. Is that also correct? No. Yeah, so they're the same. And probably the easiest way to see it is if you factor out a -1 from numerator and denominator of either one of them and then cancel, you'll get the other. So let me give you an example that you've probably run into before. When you're finding the slope of between 2 points, this is probably not what you're used to seeing, but can I do this? Is there any rule when you're calculating slope that I have to have a point? All you're doing, if you're I will say this though, you need to be consistent, otherwise you're gonna be wrong. Basically, all you're really doing is changing the way you're subtracting. But if you do that in both places, you're really just, those two things are gonna undo each other. So all of that to say, no, if you move things to the other side, you're gonna get something that's mathematically equivalent. You're gonna be fine. Any questions here? Okay. All right, so given this equation we just looked at, we want to find where the tangent is horizontal. And I'm going to need someone to remind me what we came up with. What was dy dx just now? So now I want to find where the tangent is horizontal. What does that mean about dy dx? What's that? Yep, this thing's equal to 0. So think about what the derivative tells you. Up here in the margin, I'll draw a curve. Here would have a horizontal tangent. What's the derivative of that curve going to be where I drew that tangent line? 0. So horizontal slope, if you see a line of a horizontal, right? Are we okay with that, or do we need to go into more detail about that? But yeah, but the points where the tangent is horizontal, that's going to be where dy dx or f prime, y prime, the derivative is going to be equal to 0. All right, can I go a little further in solving this thing? Are we okay if I say this? X squared minus 2y equals 0. How come I can ignore that? How come I can just throw out the denominator like that? Right. So yeah, I have to be dividing 0 by something non-zero. So from here, I can get this x squared equals 2y, or y equals x squared over 2. So remember, looking for those xy points where this tangent is horizontal, and working from the fact that the derivative has to be 0, I have found this other way, this other equivalent way of finding those points. It's anywhere where y equals 1/2 x squared. In this case, are we okay with why those are the same thing now? Basically, the only way the derivative can be equal to 0 is if y is equal to x squared over 2. So that allows me to do this. I'm going to take this equation, which I can't really solve because it's got 2 variables in it, but now I have a way to write it in terms of only one. So I have x cubed plus x squared over 2 cubed equals 6x times x squared over 2. Is this an equation I can solve? Yep. Got a single variable in it, so let's clean it up a little bit. X cubed plus 1/8 x to the 6th equals 3x cubed. So 1/8 x to the 6th minus 2x cubed equals 0. I don't like the fraction, so I'll multiply both sides by 8. All right, how we solve that thing from there? Sebastian, go ahead. I don't want to divide by x cubed, but there is something similar I can do. Why do I not want to divide by x cubed? Oh, you meant factoring? I'm going to guess that a few of you in here want to just divide out by, basically divide by x cubed. The reason that is dangerous is because you lose solutions. If you divide by x cubed, then you'll just get the equation x cubed minus 16 equals 0, which will give you some solutions, but you'll lose a lot too. From here, what do I know about, can I solve for x now? I get x equals 0 and x equals cube root of 16. I'll pause for a second here. Any questions about how we got those x values? So now I need to find the y values that go with them. So one of these points is going to be the origin. Because of x equals 0, then y equals 0 squared over 2. And the other point is going to be this thing, cube root of 16 and 16 to the 2/3 power over 2. Are we okay with both of those points? I think that I have to throw the origin out. Why is that? So what? Sorry, you said it's over 0. What am I? Where am I divided by 0? In the derivative, right? So the point, the origin. So I. Now, are we okay that this other one's all right? This should be good. So we actually only found one point where that was true. I'll pause for a minute if you have any questions before we go on. We getting a handle on the implicit differentiation thing? Sure. Are you okay with x being equal to the cube root of 16? Okay. So then remember this whole search here where I got this this equation with two variables down to one variable comes from y equals x squared over 2. So y equals the cube root of 16 squared over 2. And I just basically just rewrote that that root as a fractional power. Anything else? All right. Get some trig involved. So I want to find y prime given this equation. So looking at the left-hand side, so I need to use the chain rule. Do I have a composite function that I'm dealing with? On the left-hand side, sorry. Right, so definitely gonna need the chain rule on the left-hand side. Anything else? So I don't think there's anything else. I mean, chain rule we're gonna have to involve maybe even in more than 2 layers, but if I'm looking at sine of x plus y, what's my outermost function there? Sine. So if I'm going to take the derivative with respect to x of sine of x plus y, how is that going to start? Cosine of x plus y, so that's the derivative of the outside function, which definitely is important. What else? Okay, then you're going to multiply that by x of x plus y. What is the derivative with respect to x of x plus y? I heard a vote for dy dx, but it's going to be a little bit more 1 plus dy dx. You know what? I am asking for y prime this time, so let's go ahead and just use that notation to start. So that's the left-hand side. Are we okay with that? Go ahead. Okay, so a couple things there. The derivative of x plus y is not 1 plus y, but 1 plus y prime. And just a reminder, I'm using y prime to stand in for dy dx. So pretty subtle, but you're going to see. Make sure I use it too. That's first thing. It's not 1 plus y, it's y prime. But if you look at that derivative of x plus y, because they're added together, I can do this. We take the derivative with respect to x of x plus the derivative with respect to x of y. So the derivative of x is just 1. And the derivative of y with respect to x is, by definition, dy dx. In this case, we're calling it y prime, but it's the same idea. Any more questions about the left-hand side? All right, right-hand side, y squared cosine x. How can we handle that? What rules do we need? Go ahead, Thomas. We're gonna need product rule, right? We have, let's call it u and v again. Most logical way to split those up is u equals y squared and v equals cosine x. So then what is du dx? Go ahead, Thomas. 2y times y prime. So outside function is that squaring, so 2y. And then I'm differentiating y with respect to x, so I need to include that dy dx term, or y prime. All right, then what's dv dx? Negative sine x. So those are all the ingredients we need. So I've got cosine of x plus y times 1 plus y prime equals 2 cosine x y y prime minus y squared sine x, and I better pause there. Anything that looks wrong in there, we speak up, because it very well could be. Let's question. So you know, when it's all in one variable, it's quite a lot easier to see. But really, what you have here is, so I have this relationship: x goes into whatever this process is that maps x to y. So that's one function, and then the other one is the one that's a little more plain to see, which is squaring. So the first derivative you take is the squaring. Anytime you're doing this anytime you're taking the derivative with respect to x of some other variable, in this case it's been y, chain rule is going to get involved. Because it's implicit, it's implied, but there is a nested function there, whatever the function is that maps x to y. Any more questions about this derivative so far? Which, in the interest of time, I might just eject from right now. Yeah, I better do that. So I'm gonna leave as an exercise to solve for y prime. So a couple of different tasks that are going on here, and they're both difficult, but they're both, I think, pretty different. Number one is the calculus involved, where you have to take derivative, which we've done. The second one is explicitly stating what that derivative is, for basically using the algebra you need to isolate. So we've seen an example of that. I really need to show you a second derivative example before we get out of here, though. So x to the fourth plus y to the fourth equals 16. I want to find y double prime. So if I want to find y double prime, what must I do first? I got to find y prime. So first we're going to find y prime. So let's do that. Now we're going to take we got to implicitly differentiate both sides. What's the derivative of the left-hand side with respect to x going to be? Plus 4y prime. Equals 16. Absolutely. So that's 0. Anything else, Thomas? Yep. So, and I'm glad that, so one thing I wanted to highlight here is that it's not a coincidence that the derivative, basically the derivative of those two terms look so similar. So x to the fourth, that's just no real composition going on there. I am taking x, raising to the 4th power. I understand the derivative. That same function's involved in y to the 4th, except there's that other implied function, whatever the function is that maps x to y. So that's why you're seeing this chain rule process taking place. All right, are we okay with this derivative now? You could. It's usually not pretty. This one is not going to be that bad if we tried that. In fact, if we hustle a little bit, maybe we can see both. But let's actually isolate y prime here. So I can divide both sides by 4. If I bring over, is it negative y cubed over x cubed? Or did I flip them? I did, didn't I? All right, so we have an expression now for y prime. So in order to find y double prime, what would I do from there? Basically, I can just take the derivative of both sides again with respect to x. Left-hand side just becomes y double prime. How about the right-hand side? What rule am I going to have to use? I have negative x cubed over y cubed. What rule am I going to have to take advantage of? Yeah, I got a function divided by another function, so I'm underneath the quotient rule. So let's split that up. So I got u equals negative x cubed. V equals y cubed, which means du dx is equal to negative 3x squared. And dv dx is going to be equal to 3y squared y prime. So doing all the pieces of the quotient rule, so I got negative 3x squared times y cubed minus negative x cubed times 3y squared y prime all over y to the 6th. One little problem before I finish up here. I have y double prime, which is in terms of x and y's, which is fine, but it's also in terms of y prime, which I would like not to have to define my second derivative using my first derivative. So what can I do about that? Thomas? Yep. So I know what y prime is. That was the first thing I did. So simplifying there. And gonna leave it looking really unsimplified, but that's okay. Any questions on this guy getting into the second derivative? All right. I'll stick around for a few minutes if you have any questions. Otherwise, I'll see you tomorrow or see you Wednesday. Yep.